Okay, welcome back. So we're going to talk now about maximum parsimony methods, and a word that is synonymous for maximum parsimony is minimum evolution. These models, this family of inference techniques is based on the belief that is quite similar to the quote that I gave earlier by Einstein, saying more or less that the best model is the simplest. So the belief is that the best way to account for what you see in terms of the traits on the leaves of your phylogeny, the best way to account for this is the one that involves the minimum number of substitutions on the branches. Okay, so we're going to try and explain the extant sequences with as few evolutionary events, and there will be character substitutions, deletions and insertions in a broader sense, but in aligned sequences with no gaps, it's going to be only character substitutions. So as few evolutionary events as possible. Okay, the minimum count of events, number of events, in order to produce what you see as the traits on the leaves of your tree, this minimum count of events is called parsimony cost or parsimony steps. Okay. So in a way, it's similar to trying to get a tree with smallest total branch length. Okay, that's akin to this. If you define the length of a branch in this version in minimum in parsimony trees to be like the sum of the events that have occurred on that branch, the total number of evolutionary events that have occurred on that branch. So the basis, the rationale for minimum evolution techniques is just a dogma. It's not a scientific truth. Okay, it's a belief in a way. It's a guess. Let's try and guess the evolutionary history with the minimum amount of evolutionary events. Okay. And you remember, you know that the true number of substitutions is bigger than the inferred parsimony cost, because you remember I said that the evolutionary distance is bigger or equal than the one that we inferred with the naive edit distance that is based on only the observed differences. Okay, think of the possible evolutionary history of A mutating into a T and then mutating back into an A. If you see the extant taxa A, and then you see that the parsimony cost is 0, but in fact there have been 2 evolutionary events. Yeah. Okay, so you have to be very cautious with the maximum parsimony phylogenies on very divergent data. If you know that you're trying to build a phylogeny on species that are extremely far from each other, then you know that it's not true that the real history is the one with the minimum amount of substitutions, or it will tend not to be true because your species or your taxa diverged, evolutionarily speaking, diverged a lot from each other. So beware, and usually maximum parsimony phylogenies are not the best tool to explain evolutionary history, including very divergent taxa. So let's have in this series of slides very simple examples where I have only one site in an alignment. Okay, I'm just talking about one site in a nucleotide alignment. So we have these 4 taxa. We have 4 taxa, and we have 4 characters corresponding to these 4 taxa, ACCA. Okay. And I'll have different tree topologies. So in this first tree topology, I will show you, okay, with this blue bars, it's my guess at the fact that an evolutionary event of substitution occurred there, somewhere there on this branch, okay? And in gray, I put what is, according to my belief, consistent with my placement of the blue bars, what would be the ancestral character there, okay? So here, for instance, if I say, okay, I guess that here there was an evolutionary substitution between C and A, and remember that I want to have the minimum amount of evolutionary events, the minimum number of evolutionary events, the minimum number of blue bars, right? So I could put 2 bars here and say here this was a G and this was a G, so here I had 1 bar because this G mutated into a C, and my 2 bars comes from the fact that I expect that maybe A changed to T and this T changed to G, etc. But no, that's not the route we want to take. We want to explain what we see with the minimum number of mutations. So this is one possible explanation on this tree. And this possible explanation involves 2 events of substitution, okay? And the ancestral character here is C, and it's also C here. Notice that I could say, okay, this ancestral character is A, and then I would move my blue bar from this branch to this branch, okay? I would still have a history and explanation of what I see on the leaves, this explanation using 2 evolutionary events, right? Okay. And it's easy to, it's easy to get convinced that with this tree, I cannot explain what I see with fewer than 2 evolutionary events. You can just try lots of different histories and you'll see you cannot reach a cost that is less than 2. In this tree here, it's always the same taxa, but if I have this new tree topology, linking AC here and linking CA here, with the root being here, then the cost is also equal to 2. The minimum cost is equal to 2. And one possible explanation would be ancestral character C here, ancestral character C here, 1 event of mutation from C to A over time, and 1 event of mutation from C to A here, and no event of mutation here, okay? Because since we want to have the minimum number of events, it makes no sense to say here I have 1 mutation, then you would need to add another one back to C, right? Now, if I present this phylogeny, this different topology linking the different characters, then you see that here, the ancestral character could be C here, and the ancestral character here could be A, and then with this possible history, you would need only 1 evolutionary event here, right? From A to C, sorry, 1 substitution. So we see that the minimum cost with this tree, evolutionary cost is 1, while with this tree the minimum cost is 2, and with this tree the minimum cost is 2, right? So different trees give you different parsimony costs most of the time. So if we had only this one site as our input data, and if we were using the minimum evolution paradigm, then we would decide for this tree. And we would say, okay, I decide for this tree, and my total cost for this tree is equal to 1. And for me, it would be the most probable evolutionary history, this one, right? So different sites here in the previous slide, we used only 1 site, but you understand that in an alignment you will have many sites, and these different sites may support in a way different trees. Okay, so maybe using 1 tree you would have a cost of 3 for site number 1, and a cost of 0 for site number 2. And using a different tree, you would have a cost of 0 for site number 1 and a cost of 5 for site number 2, for instance. Okay, so different sites support in a way different trees. And the total parsimony cost will be the sum of the costs, the sum of the individual costs of each site. And this is the paradigm of independent sites that we will find again in maximum likelihood methods. So because the phylogeny must build from a multiple sequence alignment in most cases, it must take into account all the sites, and we use this, okay, this formula. The total parsimony cost is the sum on all the sites. So it's which tree or which tree topology will be chosen will be the one that on average on all sites produces the lowest cost. It's interesting to see that in some sites, and we say don't choose, okay? Some sites are said to be uninformative from the viewpoint of maximum parsimony because they will not help you decide what's the most parsimonious tree. And these sites are of different nature. First, see the conserved site, the example of a conserved site. If your site is conserved, it means that it's a column in your alignment with identical characters all the way. From top to bottom of the column, you have only one character. Then, whichever topology you choose here, you will you will say, okay, all the ancestral characters are equal to this single character seen on the leaves, and then my parsimony cost for the whole tree is equal to 0. Okay, it makes sense. And this cost of 0 will be conserved and will be the one for any tree you choose. Whatever the topology you choose, the minimum evolution cost on that tree will be equal to 0. Right, that's obvious. If you have what we call an n-1 consensus, if you have a column or a site with all characters being equal except one, okay? Then for all trees, you will have one history, at least one history, in fact exactly one, with a cost of 1, okay? And it's easy to understand how to build that history. Just put one mutation, or in all the internal nodes, you replicate the character that is seen on all leaves but one. So that's the character you will put in the internal nodes, here G. And there is only one branch on which you put a bar to signal a substitution, is the terminal branch leading to the non-G leaf, okay? In this case, this one. So then you see that you will be able to perform this process, whatever the tree is, whatever the tree topology is. So for any tree, you will have a cost of 1. In case your site is a site of so-called n-1 consensus. Another example of a site that doesn't help you choose amongst trees is an n-2 consensus with unique characters. Okay, unique characters meaning that you have n characters that are you have n-2 characters that are identical. Here I could have many other G's, and then I have the 2 characters that are not G's. They are different from each other, okay? It's A and C. It's not 2 T's, for instance, or it's not 2 A's, or it's not 2 C's. It's 2 different characters. Then you can figure out easily that whatever the tree you will build, you will find a history with 2 evolutionary events, okay? And this history also has G on all internal nodes, and evolutionary events of substitution on the terminal branches leading to the 2 non-consensus characters. Okay, so some sites are not informative in order for us to decide which is the best or the most parsimonious tree. So in an analysis of maximum parsimony, it's good to filter out these sites first and foremost. You will filter out these sites, but you will remember what the costs they bring to you. Okay, because at the end, the total parsimony cost for the tree, or for the alignment, or for the tree on that alignment, is the sum of the parsimony costs generated by each site. So this parsimony cost of 1, you will keep it, it will appear in the final sum. This parsimony cost of 2, it will appear also in the final sum. But what we are saying here on this slide is that these type of sites will not help you decide which is the most parsimonious tree. Other uninformative sites, an n-2 consensus with unique cars, so that's another example of what we've seen earlier, with another history, possible history with cost 2. Here, instead of saying it's G here, I could say it's a C. In this case, I have an evolutionary event here and another evolutionary event here. It doesn't modify the total cost, the cost is 2, okay? Here also another type of history. Here I put G, but here the C and the A, the difference between this and the previous slides is that the C and the A were not neighbors, are not neighbors, sorry, in this example, while they were neighbors in the previous example. It doesn't change the fact that the cost is equal to 2, and here I show you how you get this cost with 2 events of substitution. Here in this case you have no pairs of identical characters. Why do I say no 2 pairs of identical characters? You have no pair of identical characters. You have the 4 different characters, and necessarily here you will have a cost equal to 3 for all the trees. Okay, on this example of 4 characters, all being different. Whatever the labels you put on the internal nodes, you will find an evolutionary, you will find an evolutionary history with 3, the minimum evolutionary history with 3 events of substitution. So we've seen non-informative sites, and so since researchers have been interested in the maximum parsimony approach, they have been able to devise a definition for what an informative site is for maximum parsimony. A site is informative for maximum parsimony if and only if it contains at least 2 different characters in at least 2 copies each. Okay, so MP methods ignore potentially many sites, which is something that makes them also fast, that adds to their rapidity. So at least 2 different characters in at least 2 copies each, and then you have an informative site, a site that will help you decide which is the best tree in terms of maximum parsimony. So core to the maximum parsimony analysis is Fitch's algorithm, and it was published in 1971. It's a very fast algorithm to calculate the parsimony score for any given site on any given tree. So the tree is given. This algorithm, Fitch's algorithm, doesn't help you explore what is the best, explore the space of trees. But if you give me a given tree, if you give me a given site, so a given tree plus labels on the leaves, so characters on the OTUs, then I can calculate easily, thanks to Fitch's algorithm, the parsimony score. And what is interesting is that it gives both the parsimony score and a most parsimonious history. So a set of ancestral characters with which to label the internal nodes of your tree. And this is done in linear time. So again, it doesn't search the space of the different phylogenies or the different tree topologies. It's a mere calculation on a given tree. So let's have a last break before we see how it works.